In the lesson today, we're going to be taking a look at the random variables which are discrete and how we can start to discuss probability related to discrete random variables. We're going to do this through probability distributions and introduce the concept of a probability distribution function or probability mass function. So with today's lesson, we want to define what a probability mass function is, and we'll illustrate how it's used. We also want to understand what are the properties of a valid PMF. So just like we had the axioms or the properties that defined valid probabilities generally, we're going to have valid PMFs. We want to be able to interpret the PMF as well as any parameters that might be associated with it. We also are going to introduce and we'd like to understand the concept of a cumulative distribution function. And then we'll introduce two specific discrete distributions, the Bernoulli and the geometric distributions. And so really what we're trying to do today is introduce how we think about discrete random variables, which were brought forth in the last lesson. So the first thing that I want to do today is start with a fairly blanket statement, which is to say that there's no probabilistic difference between modeling a coin flip and modeling a plane crash. And so what do I mean by this? Well, whether you're talking about flipping a coin or you're talking about seeing whether or not a plane is going to make a safe landing, really what you're thinking about there is a process that has two outcomes, right? You can either get a heads or tails on the coin flip, you can get a safe landing or a crash on the plane crash. Of course, there's plenty more that goes into whether or not the plane makes a safe landing. But in terms of the actual outcome space that we're thinking about, they're binary in both cases. And what we're interested in typically is if you're flipping a coin, what's the probability you get a heads? And if you're flying a plane, what's the probability that it lands safely? And so at the end of the day, once we've abstracted away to the concept of random variables, once we've sort of removed the specifics of the experiment, the underlying probability is going to be modeled in the same way. We're going to be able to think about it mathematically in the same way. And this partly explains why statisticians and probabilists are so set on using examples like flipping coins, like drawing cards, like drawing balls out of an urn, if you've seen any of these types of questions. But it also sort of allows us to reason about very complex scenarios by using the tools from these more simplified cases. And so, again, I'll just reiterate that from a probabilistic perspective, modeling a coin flip, modeling a plane crash, that's basically the same thing. And what we're going to do in today's lesson is try to give ourselves some tools to be able to do either of these things. So, as a slight recap, we know that the probability over the whole sample space is going to be equal to 1. So we can write that as P of S equals 1. The idea with a probability distribution, and recall that we saw distributions for a data set, and so probability distribution sort of generalizes this a little bit more, is that we want to split up this total probability to each of the outcomes. So we want to allocate probability to each of the possible events, and we know that at the end of the day, all of the events have to sum up to 1. So we can think about this sort of visually represented as a histogram, except instead of it being the histogram for some specific data set, we're thinking about it as the true histogram, right? So the actual underlying process will have some corresponding histogram, and the probability distribution is going to be sort of represented by that histogram. We're often thinking about distributions being associated to random variables, right? So we could think about the distribution for the number of heads in a certain number of flips of a coin, right? And so once you have a random variable, you can ask, what is this random variable's distribution? And that's how we'll typically talk about it. And when we have distributions, we're either thinking of them as being discrete or continuous. And so if you have a discrete random variable, it's going to have a discrete probability distribution. And that's what we're focused on today. In several lessons, we'll start looking at continuous probability distributions as well. Discrete probability distributions are characterized by what we call the probability mass function. Okay, so if you have a discrete distribution, we're going to be able to represent that mathematically through this probability mass function. So a probability mass function, or a PMF, is a mathematical function which assigns a numeric value to each outcome that a random variable can take on. So it says what's the probability of the first outcome, some value, second outcome, some value, and so forth. So if we think that, or if we suppose that a random variable can take on x1, x2, and so on, all a PMF does is assigns a specific value to each xi. So it says the probability that xi is some set value. Now, in the same way that we required sort of results from true probabilities, just basic probabilities, we require results from the PMF as well. So in order for the PMF to be valid, we know that the probability will have to fall between 0 and 1, and we know that it's going to have to sum up to be 1, right? So it's how is the probability distributed over all of the possible events. And if we think back to our frequentist interpretation of probability, what we're really saying is that in some proportion of events, so in pxi proportion of the experiments, then we would expect to observe xi as the outcome for that experiment. And that's what the PMF really is representing. Now, oftentimes, instead of just assigning a numeric value, right? So x1 has a certain probability, x2 has a certain probability, and so forth. Oftentimes, we'll actually try to express this through some sort of mathematical function. And if that's the case, then we're frequently going to need parameters, which are going to control these different probabilities at different events, right? And so if you have a distribution which is characterized by a parameter, you could think about changing that parameter, which is going to give you a different distribution, but ultimately it's all going to come from the same family of distributions. So any distributions that differ only in the parameter values are from the same family. And we'll see some examples of what I mean by this very soon. In terms of notation, if P of x is going to be the PMF for a distribution, then we can write x and then this tilde P of x to say that x is distributed according to that distribution. And what we mean by that is that the values that we're going to observe of the random variable x are going to follow this probability distribution. So let's make this concrete with an example, and it's probably the most simple example we can use, and it's the example from the plane crash and coin flip from the beginning. So if we have a random variable that only takes on two values, say a 0 and a 1, then this is going to follow what we call a Bernoulli distribution. The PMF of a Bernoulli distribution is going to be characterized by a parameter p, and we can say that the probability that it equals x is going to be given by this expression here. Now there's actually a very slight typo in this expression here. And so the idea is that the probability that we get 1, we want it to equal p, and the probability that we get 0 has to therefore be 1 minus p, right? And so this expression should actually be probability of x equals p to the x, 1 minus p to the 1 minus x there. And so I should correct these before they're up online, but if the mistake is still in the slides, take a look at that correction there. But this right here is going to be our PMF for the Bernoulli distribution. And the idea is that any value that we assign for p, right, so p has to be a value between 0 and 1, is going to give us a specific Bernoulli distribution. And all of the different Bernoulli distributions are going to be from the same family, the Bernoulli family. But this fully captures all of the events that can happen for a Bernoulli random variable. Often, when we're thinking about Bernoulli distributions, we're going to think about the value of 1 as being a success and the value of 0 as being a failure. We use that language even when it's not necessarily the most appropriate. So, for instance, modeling whether a plane lands safely as a success or a failure may be valid. Sometimes we'll say that we call flipping a head a success, right? And that's just the language that comes up because very often we're using this to think about success and failure as the sort of binary options there. Now, We've introduced the probability mass function. We also have the concept of a cumulative distribution function. So this is going to be a related quantity, and it's going to give us the probability that a variable takes on a value which is less than or equal to some threshold. So we'd say that the probability that x is less than or equal to x. We denote this probability using a capital F, and then sometimes we'll write the subscript of the random variable that we're talking about. And this is going to be the summation of all possible values from negative infinity up to x. Now, of course, oftentimes we're not going to be able to take on negative infinity as a value, right? If 0 is the lowest value, then it's just going to be, 0 through x. But the idea is that this gives us what's the probability that we observe something which is less than or equal to x. In a discrete case, the CDF is going to be a step function all of the time. So we're going to see sort of the jumps at the different values that it can take. And an important point is that we can always interchange between a PMF and a CDF. And so in this way, a CDF is going to characterize a distribution just as a PMF does, right? So every distribution is going to have a PMF. Every discrete distribution is going to have a CDF as well. And we can use the CDF to compute the probability of falling inside of an interval. So if you want to know what's the chances that our random variable falls between two endpoints, then we can use a difference of CDFs, right? And you should be able to convince yourself that this is true. But the idea is basically that there's enough times that we're thinking about probability of being less than or equal to some threshold. And so we want to give this sort of a special name. They will come up more when we're thinking about continuous random variables, but it's useful to introduce them in the case of discrete random variables as well. Generally speaking, when we're doing calculations, it's often going to be easier to work with our CDF. But with discrete distributions, it's also often going to be the case that we don't get a closed form expression for the CDF. And so in that case, we have to choose what's going to make the most sense. When we talked about the CDF being a step function, this is the idea that we have in mind, right? And so you can see that below 0, there's no probability. And then at 0, some probability threshold, right? And so then we make that jump. But then there's no difference between x falling below 0 or below some threshold just below 1. But then at 1, we see another jump, right? And at 2, we see another jump. And so here, what we can see is that there's going to be different probabilities of observing 0 or 1 or 2 and so forth. And we could actually read off what are those probabilities by thinking about the difference in the step function at each of those places, right? But so every discrete distribution is going to have a CDF that looks like this. In the continuous case, they become a little bit more interesting. So we saw the Bernoulli distribution. Another common distribution that we're going to be thinking about is the geometric distribution. And so the way to think about a geometric distribution is to start flipping a coin, right? And we're going to keep flipping until we get a heads. And we want to know how many times did we have to flip this coin until we got heads. Any process that follows that same type of procedure of repeating an experiment until you get some outcome that you're interested in is going to follow the geometric distribution. Now, it's related to the Bernoulli distribution, right? Because we're performing repeated Bernoulli trials. We have two outcomes here, and we're waiting until we get a success, but it's not going to be exactly the Bernoulli distribution. It's also going to be governed by a parameter p, and this parameter is also going to be read as the success parameter for the distribution, right? So it's going to be what's the probability of observing a success. And the PMF of the distribution is actually going to look somewhat similar, right? So in this case, we're going to say that the probability that we observe x total trials is going to be, or x failures until the success is going to be given by 1 minus p to the power of x minus 1 times by p, where p is the probability of observing a success on any different trial, right? And so the probability that you observe your first, so x equals 1 is the first heads, is going to, you plug in x equals 1 here, the exponents are going to cancel out, and you're just left with p. And then if you want it to be 2, you can work out the probability and so on. And then x is going to be any value 1 or greater. any integer value. Sometimes you'll see this rewritten instead of taking x minus 1 to just be 1 minus p to the power x times by p. And in this case, x is now representing how many failures were there until the first success, right? So you can sort of interchange between those. Now, we can actually write down directly what the CDF is going to be in this case. In order to do so, we need this concept of the lower integer, right? And so if we sort of take a look here, we use this floor notation to be the integer value, which is less than or equal to x, and it's the closest integer in that case. So for instance, if we take, say, the floor of 1.7, that's going to be equal to 1, because the lowest integer less than 1.7 is equal to 1 exactly. Okay. So the general concept from today's lesson is that distributions are going to be our way of breaking down the probability values for different random variables. When we have a discrete distribution, that's going to be characterized by a PMF. We can also look at the CDF, which is going to give us the probability that we take on at most a particular value. We looked at the Bernoulli distribution, which characterizes success or failures on a single experiment. And we looked at the geometric distribution that models repeated success-failure experiments until the first time that we reach a success. Right? We saw that those form two different families, each of them parameterized by the same parameter. Right? In the coming lessons, we're going to take a deeper look into discrete random variables, discrete probability distributions, and then we're going to consider these same types of topics for the continuous case. And so I would encourage you all to go and try to look at some of these topics in a little bit more depth, play around with some of the different concepts that we covered, and then in the next lesson, we'll sort of go deeper with all of them. So I hope to see you all in the next lesson.